Today we are going to explore a fascinating chapter of human history, a journey through the technological achievements of the Roman Empire that defied time and continue to impress engineers and scientists to this day. Before continuing with the video, remember to subscribe to the channel for more documentary narratives like this one. The year was approximately 312 before Christ when the first Roman workers began to excavate the earth around the city of Rome. At that moment, under the scorching Mediterranean sun, they could not imagine that they were about to create something that would survive for more than 2 millennia. The Roman civilization was about to solve one of the greatest challenges that any urban society has ever faced: how to bring clean and abundant water to hundreds of thousands of people concentrated in a single place. The solution they developed would not only solve this immediate problem, but would establish engineering standards that would serve as a reference for centuries. The Roman aqueducts were born from a practical necessity, but they transformed into monuments to engineering that even today provoke genuine admiration among specialists from all over the world. When Roman engineers were faced with the problem of supplying exponentially growing cities, they did not resort to improvised or temporary solutions. Instead, they developed a system that exclusively utilized the force of gravity to transport millions of liters of water across distances that would seem impossible for any other civilization of the time. The elegance of this solution resided precisely in its apparent simplicity. The first aqueduct of Rome, known as Aqua Appia, was built in 312 before Christ and extended for approximately 16 kilometers. Its builder, Appius Claudius Caecus, could not have predicted that he was inaugurating a tradition of hydraulic engineering that would define the Roman civilization. In the following centuries, the Romans would build a network of 11 main aqueducts that together totaled more than 400 kilometers in length, providing water for a population that would reach more than 1 million inhabitants at the height of the empire. This scale of supply would not be equaled in any other city in the world for more than 1,500 years. The engineering behind these structures revealed a surprisingly advanced mathematical knowledge for the time. Roman engineers calculated the necessary slope with a precision that would leave many modern professionals impressed. The typical gradient was only half a meter for every kilometer of length, a slope so subtle that any calculation error would compromise the entire system. If the slope were too steep, the water would run too fast and damage the channels over time. If it were too gentle, the water would simply stop flowing or accumulate in low points. The margin for error was practically non-existent. To cross valleys and depressions in the terrain, the Romans erected monumental arcades that became enduring symbols of their civilization and inspired generations of architects. The Aqueduct of Segovia in present-day Spain rose to almost 30 meters in height and was built with granite blocks stacked without any mortar. Each stone was cut with such precision that it fit perfectly into the next, creating a structure that resisted earthquakes, invasions, weather, and centuries of neglect. Today, almost 2,000 years after its construction, it still stands intact over the Spanish city, serving as a silent testimony to Roman mastery. The concrete that the Romans used to line their aqueducts represented another remarkable technological feat that we have only recently begun to fully understand. They developed a special mixture that incorporated volcanic ash from the vicinity of Mount Vesuvius, creating a waterproof material that became more resistant over time, unlike modern materials. This hydraulic cement, as contemporary scientists call it, had the surprising ability to harden even when submerged in water, a property that confounded researchers for centuries. While clean water flowed into Roman cities through the aqueducts, engineers faced an equally complex challenge: how to remove all the dirty water and waste that a large population inevitably produced. The answer came in the form of one of the most ambitious sanitation systems the ancient world has ever witnessed, a work that remains functional to this day. The Cloaca Maxima, whose name in Latin simply means the Great Sewer, began as a modest drainage channel in the 6th century before Christ. Its initial purpose was to drain the marshy waters of the valley where the Roman Forum was located, transforming a waterlogged terrain into usable space for construction and commerce. But the Romans, with their characteristic ambition to do everything on a large scale, were not satisfied with a temporary solution. Over the following centuries, the Cloaca Maxima was continuously expanded and improved until it became an underground network that stretched throughout the city. The main tunnels were so wide that they allowed the passage of boats, with some sections measuring more than 3 meters in width and height. Workers could walk through these passages to perform inspections and maintenance, a practice that continued even after the fall of the empire and that persists in some areas to this day. The construction of these galleries demonstrated the same technical mastery that characterized the aqueducts. The Romans used carefully cut stone blocks to form arches that distributed weight uniformly, preventing collapse even under the weight of buildings constructed above. In some sections, the builders completely dispensed with the use of mortar, relying solely on the precision of the stone cutting to keep the structure together for millennia. The sanitary importance of this system cannot be underestimated. In a time when the relationship between dirt and disease was not yet scientifically understood, the Romans observed empirically that well-drained cities were healthier. The Cloaca Maxima and its branches helped prevent the accumulation of stagnant water, reducing the proliferation of mosquitoes and other disease vectors. During the hot Mediterranean summers, when other cities suffered from epidemics caused by the decomposition of waste in the open air, Rome managed to maintain relatively hygienic conditions for its population. Significant portions of the original Cloaca Maxima continue to function to this day, almost 3,000 years after its initial construction. Archaeologists and engineers who descend into the tunnels are impressed by the quality of the masonry and the solidity of the structures, which still fulfill their function of draining water from the streets of modern Rome. Few contemporary infrastructure works can aspire to a similar longevity. During the harsh winters that occasionally hit even the Mediterranean regions, keeping environments warm presented another considerable technical challenge. The hypocaust, a term derived from the Greek meaning fire from below, represented a central heating system that anticipated modern climate control technologies by almost 2 millennia. The idea was ingeniously simple in concept, but required meticulous execution. In practice, the construction of a hypocaust required careful planning from the building's foundations. The floor was raised on small brick columns called pilae, which created a space approximately 60 centimeters high. An external furnace, usually fueled by wood or coal, produced hot air that was forced through this empty space by the simple pressure of continuous combustion. The heat then radiated through the floor, heating the environment above gradually and uniformly. In addition to the raised floor, Roman engineers built hollow ceramic tubes embedded in the walls themselves, creating vertical channels through which hot air could rise naturally. This allowed for heating not only the floor, but also the vertical surfaces, distributing heat even more efficiently throughout the environment. The entire system worked without pumps, without motors, without any mechanical component that could break, just physics and architecture working in harmony. The great Roman public baths utilized the hypocaust in a particularly sophisticated way. Architects created differentiated temperature zones, from cold water rooms to almost scalding environments, simply by varying the proximity to the furnace and the intensity of air circulation. A bather could go through a sequence of progressively warmer environments, an experience that prefigured modern spas and saunas. Some systems discovered in European archaeological sites still show signs that they could work if they were reactivated, even after almost 2,000 years of neglect. While the Romans mastered the art of moving and heating water, they also discovered that moving water could be used as a source of energy to perform work that would otherwise require considerable human or animal effort. This discovery would lead to the development of technologies that some historians consider precursors to the Industrial Revolution. Roman water wheels represented an ingenious application of basic physical principles. The idea of using running water to turn a wheel existed in other civilizations, but the Romans developed and applied it on an unprecedented industrial scale. They built wooden wheels that could reach more than 6 meters in height, strategically positioned in rivers and channels to capture the energy of the water flow continuously. Roman engineers developed 2 main types of water wheels, each adapted to specific conditions of the terrain and the watercourse. Undershot wheels worked with the current hitting the paddles from the bottom, mainly taking advantage of the horizontal velocity of the flow. In contrast, Overshot wheels received water poured from above, combining the energy of movement with the weight of the water itself to generate even more force. This second variant could achieve surprising efficiencies, converting up to 70% of the available hydraulic energy into useful mechanical work. The most common application of these wheels was in the milling of grains. Water-powered mills could process quantities of wheat that would be impossible to achieve with hand mills, producing enough flour to feed entire cities. A single Roman hydraulic mill could perform the work of dozens of slaves, freeing up labor for other activities and reducing the production costs of basic foods. The Barbigel Mill Complex, located in the south of present-day France, offers an impressive example of the scale these operations could reach. Built in the 2nd century of the Christian era, the complex consisted of 16 water wheels, organized in 2 parallel rows, fed by an aqueduct specially built for this purpose. Historians estimate that this installation could produce enough flour to supply a city of up to 30,000 inhabitants, working continuously day and night, without the need for human or animal power to drive the mills. If water wheels demonstrated Roman mastery over natural forces in motion, their concrete revealed an equally deep understanding of material chemistry. The secret of the extraordinary longevity of Roman structures remained a mystery for centuries, until modern scientific research began to unravel the unique composition of this ancient material. Roman concrete differed fundamentally from modern mixtures in its basic composition. While contemporary cement uses limestone heated to extreme temperatures, the Romans discovered that volcanic ash from the vicinity of Vesuvius and other volcanically active regions possessed extraordinary chemical properties. When mixed with lime and seawater, this ash produced a reaction that created microscopic crystals of a mineral called tobermorite, extremely resistant to erosion and wear. The most surprising aspect of this discovery is that Roman concrete becomes stronger over time, not weaker as happens with modern material. Seawater, which would normally corrode contemporary concrete in a few decades, actually contributes to the continuous formation of the crystals that strengthen the Roman structure. Scientists discovered that the hardening process continues to occur even after 2,000 years, a phenomenon that challenges the conventional logic of materials engineering. The Pantheon in Rome offers perhaps the most impressive example of the capabilities of this material. Its dome, with more than 43 meters in diameter, remains to this day the largest unreinforced concrete dome ever built in human history. The fact that it remains intact after almost 2,000 years, without the steel bars that reinforce modern structures, attests to the exceptional quality of the Roman mixture and the deep knowledge of its engineers. While concrete allowed the Romans to build on the surface of the earth, they also developed surprising techniques for working below it. Roman tunneling projects demonstrated a combination of daring ambition and mathematical precision that continues to impress modern engineers who study these endeavors. Lake Fucino, located in the center of the Italian peninsula, presented a problem that had frustrated local farmers for generations. This large lake had no natural outlet, which caused frequent floods that destroyed valuable agricultural land year after year. The Roman solution was characteristically direct and ambitious, to drill a tunnel of more than 5 kilometers through a mountain to drain the lake permanently. The execution of this project, initiated by Emperor Claudius in the 1st century of the Christian era, involved technical challenges that would test the limits of ancient engineering. Workers excavated from multiple points simultaneously, using vertical shafts to access the tunnel level and to ventilate the stale air from the underground galleries. The coordination necessary to ensure that all these separate excavations eventually met required high-precision geometric calculations. Roman surveyors used relatively simple instruments, including the groma, a rod with hanging weights to determine straight lines, and the chorobates, a leveling table that used water to check horizontal surfaces. With these basic tools and advanced mathematical knowledge, they managed to maintain the correct direction through kilometers of solid rock. When the teams finally met inside the mountain, the alignment error was only a few meters, a remarkable precision for the time and its technological limitations. The Lake Fucino project took 11 years to complete and employed approximately 30,000 workers at its peak activity. When it finally worked, It released thousands of hectares of fertile land for agriculture, transforming the regional economy and demonstrating once again the Roman capacity to reshape entire landscapes. Rising again to the surface, we find another Roman innovation that solved an apparently simple problem in an elegant way: how to move people vertically through tall buildings without wasting precious space. The answer came in the form of spiral staircases, structures that combined practical functionality with architectural sophistication. In a densely populated city like Rome, where horizontal space was extremely valuable and rents in central areas were prohibitive, the ability to move people vertically without occupying large areas of each floor represented a considerable advantage. Traditional stairs consumed precious space that could be used for housing or commerce. The mathematics involved in building an efficient spiral staircase was more complex than it might initially seem. Each step needed to be carved in a wedge shape, with the narrow part facing the center and the wide part toward the periphery. The angle of inclination, the height of each step, and the depth of the tread needed to be calculated so that the final result provided a comfortable and safe climb for users. Trajan's Column, erected in Rome at the beginning of the 2nd century, contains one of the most famous spiral staircases of antiquity. Inside this marble column of almost 40 meters in height, a staircase of 185 steps winds to the top, illuminated by small windows carved into the stone. The steps have been worn down by almost 2,000 years of visitors, but the structure remains perfectly functional, still allowing access to the viewpoint at the top of the monument. From vertical architecture, we turn our attention to innovations in food processing, where the Romans again demonstrated their ability to amplify human force through ingenious mechanisms. The screw press transformed the production of wine and olive oil, two fundamental pillars of the Mediterranean economy and diet. The principle behind the screw press was elegantly simple, converting rotary motion into linear force. A large wooden screw, carved with precision, passed through a fixed structure. When turned, the screw pushed a heavy plate down onto the material to be pressed. The mechanical advantage provided by the screw meant that one person could generate enormous pressures with relatively modest effort. With a single well-built press, a worker could process quantities of raw material that would previously have required dozens of people. The uniform and controlled pressure extracted more liquid from each batch, increasing yield and reducing waste. For a civilization that depended on olive oil not only as food, but also as fuel for lighting and an ingredient for cosmetics and medicines, this efficiency represented a significant economic advantage. The legacy of the Roman screw press extends far beyond food production. The same mechanical principle would later be applied in the Gutenberg press, which revolutionized book production in the 15th century. Some traditional wineries still use presses based on this ancestral principle. While they processed their food with sophisticated technology, the Romans also developed methods to track the passage of time, an essential resource for coordinating the activities of a complex society. Portable sundials represented an ingenious solution to the problem of keeping track of time during travel. The creation of a functional portable sundial required substantial astronomical and mathematical knowledge. The angle of the gnomon, the rod that projects the shadow, needed to be adjusted for the latitude of the place of use. The hour lines engraved on the surface varied, depending on the time of year, as the sun's trajectory changes between summer and winter. Some sophisticated models included adjustable scales or markings for different regions of the empire. The precision of these instruments, although limited by modern standards, was sufficient for the needs of the time. Merchants could estimate how much time they had before the markets closed. Lawyers knew when to present themselves in court. Travelers calculated how much distance they could still cover before nightfall. It is notable that some of these Roman portable sundials presented precision superior to the first mechanical clocks that would appear more than 1,000 years later. The Romans did not use their mastery of water and heating only for basic needs. They created public bathing experiences that combined engineering, architecture, and social organization in complexes that had no parallel in the ancient world. These establishments transformed a hygienic necessity into a cultural phenomenon that would define Roman urban life. The great baths of Rome were much more than places to wash. They functioned as community centers where citizens of all social classes could meet, do business, exercise, and socialize. The baths of Caracalla, built in the early 3rd century, could accommodate more than 1,600 bathers simultaneously, and covered an area of more than 10 hectares, including libraries, gardens, and exercise spaces. The engineering behind these complexes combined multiple Roman technologies into integrated systems. Aqueducts supplied the enormous quantities of water needed. Hypocaust systems heated the environments to varying temperatures. Drainage networks removed the used water. Bathers progressed through a carefully planned sequence of environments, from the frigidarium with its cold water tanks to the caldarium, where the almost boiling water provided an experience similar to modern saunas. The mass production of everyday objects represented another aspect of Roman technological sophistication often underestimated. The pottery known as terra sigillata demonstrated a standardized manufacturing capacity that anticipated modern industrial methods. The secret of the distinctive finish resided in a combination of ingredients and processes carefully refined over generations. Potters added powder from iron-rich minerals to the base clay, creating a mixture that developed its characteristic red color during firing. The kilns were operated in a controlled oxidizing atmosphere, with temperatures that could exceed 1,000 degrees Celsius. The precision necessary to produce consistent results required specialized knowledge passed from masters to apprentices. The durability of terra sigillata impresses to this day. Pieces recovered from archaeological sites often present intact surfaces after 2,000 years of burial, with colors still vibrant and decorations perfectly legible. This resistance to time makes Roman pottery a valuable tool for archaeologists, who can trace trade routes and occupation patterns simply by following the distribution of fragments through the ancient empire. In the area of mechanical engineering, the Romans developed solutions that reduced friction and increased the efficiency of machines and vehicles. The bearings they created demonstrated a practical understanding of physical principles that would only be formally described centuries later by scientists like Newton and his contemporaries. The ceremonial vessels found in Lake Nemi, built for Emperor Caligula in the 1st century of the Christian era, offered remarkable evidence of this technology. When archaeologists studied the remains of these enormous vessels in the 1930s, they discovered among the recovered artifacts bronze bearings that equipped the steering mechanisms, allowing massive oars to be maneuvered with relatively little effort. These bearings consisted of polished bronze cylinders positioned between concentric metal rings. When the load was applied, the cylinders rotated freely, distributing the weight and minimizing friction. The quality of the finish was impressive, with surfaces so smooth that they remained functional even after almost 2,000 years, submerged in the waters of the lake. The legacy of this technology extends directly to modern bearings, found in practically all contemporary machines. The simplest bicycle and the most advanced satellite share this technological heritage with the ceremonial ships of a Roman emperor. The fundamental principle remains unchanged. Replacing sliding friction with rolling friction dramatically reduces resistance to movement. Upon contemplating the set of these achievements, an impressive picture emerges of a civilization that combined empirical observation, mathematical skill, and practical ambition at levels rarely equaled in human history. The Romans frequently adapted and improved ideas from Greeks, Egyptians, and other civilizations that preceded them, but their unique contribution was the ability to implement these ideas on a monumental scale and with extraordinary durability. The collapse of the Western Roman Empire in the 5th century did not mean the immediate loss of all this knowledge. Many techniques continued to be practiced on a smaller scale, especially in the Eastern Roman Empire, which would survive for another 1,000 years. But the ability to execute projects of the magnitude of the aqueducts or the imperial baths disappeared for centuries. Medieval Europe would build its own wonders, but frequently with resources and knowledge inferior to what the Romans had mastered in their prime. The rediscovery and reappreciation of these ancient technologies continues to our day. Scientists study Roman concrete in search of formulas for more durable and sustainable materials. Engineers examine aqueduct systems to understand water distribution principles that can inform contemporary projects. Each discovery reinforces the perception that the Romans reached levels of technological sophistication that would only be matched many centuries after their fall. Perhaps the deepest lesson of these ancient technologies is about the nature of human progress. We often assume that history follows a linear trajectory of constant advancement, each generation automatically surpassing the previous one. But the Roman experience demonstrates that knowledge can be lost, techniques can be forgotten, and entire civilizations can regress in their capabilities. Progress is not automatic nor irreversible. The aqueducts that still carry water, the sewers that still drain cities, the concrete that still resists time, all these are tangible reminders that our ancestors were capable of extraordinary feats. They did not have computers, they did not have electricity, they did not have the vast accumulation of scientific knowledge that we possess. But they had ingenuity, determination, and a capacity to think in timescales that we, with our mentality of planned obsolescence, frequently neglect. The history of these technologies is also a history of people, although their names have rarely survived the centuries. The engineers who calculated the slopes of the aqueducts, the workers who excavated the tunnels, the potters who perfected their kilns, the blacksmiths who forged the bearings, all of them contributed to a collective legacy that transcends any individual. Their achievements speak for them through the centuries, silent but eloquent testimonies of human capacity and dedication. And so 2,000 years later, we continue to learn from them. We continue to study their techniques, to marvel at their achievements, to wonder what else they knew that we have not yet rediscovered. The Roman past is not just history, it is a repository of practical knowledge that can still inform our present and illuminate possibilities for our future. If this journey through the technological wonders of Rome has sparked your curiosity, if you found yourself imagining those ancient engineers calculating slopes under the Mediterranean sun, or those potters feeding their kilns before dawn, then I invite you to be part of this community of explorers of the past. Subscribe to the channel to follow more narratives that bring history to life, that reveal the secrets of civilizations that built the world we live in. Leave your comment sharing which of these technologies most impressed you, or which other wonder of the ancient world you would like to see explored in a future documentary. And if this content added something to your knowledge, if it made you look at a Roman bridge or an ancient ruin with new eyes, show your support by leaving your like. Each interaction helps to bring these stories to more people who, like you, believe that understanding the past is essential for building a better future. Until the next journey through history.